once again. It's the physics video lecture. Physics 203, video lecture 23. Well, we just wrapped up the Hamilton-Jacobi theory, and I'm starting something completely different as advertised. Namely, we're going to do a section on fluid mechanics. Now, that's a pretty large subject, and we only have a few lectures for it. But what I have to do is take us into fluid mechanics enough to get a little bit of the lay of the land, and then make it into wave equations. From wave equations, we're actually going to return to the Hamilton-Jacobi theory in an interesting manner. So we'll see how this goes. I think we have enough time to do everything we wanted to do. And I'll just mention a couple of resources. So an elementary resource for fluid mechanics would be your lower division undergrad textbook. So they typically have one chapter on fluid mechanics. Okay. So first of all, just your undergrad, actually lower division text. The second resource that I've based my notes on is the book by Landau and Lifshitz, which is actually pretty high level. But if you run across one of these, it's volume 6 of the course on theoretical physics. It's a huge compendium, but the initial stuff that we do was based on this book as well. So that really spans a wide range of sophistication. Good. The next thing is to just put it into the context of mechanics. And so that's the next thing I'll talk about. So we have point mechanics of a single particle, and that's Newton's law. Okay. And then we have systems of points, which is also point mechanics. Systems of point particles, so systems of point masses. How about just calling them points? Okay. And then we have m sub I, f. And in fact, we even broke it down into an external plus sum over Fij, the internal forces. That's what we had at the beginning of the semester. So we had systems of point particles as well. Something we didn't cover in this semester, but that you've certainly seen before, is rigid body mechanics. Okay. And that would be the classical mechanics that you know so far. Now, if you take the rigid body and don't require it to be completely rigid, then you have elasticity theory. And if you allow particles to behave as fluids, to slide against each other, okay, to move freely, I'm just going to write, then you have fluid mechanics. And these two can be referred to as continuum mechanics. The rigid body is, of course, also a continuum, but we just characterize it by its by a few parameters instead of as a field. So continuum mechanics, that is a field theory, and it makes use of a lot of the classical field theory concepts. So this is where we're going to be here, talking about fluid mechanics. Okay. And that's the whole system of mechanics overall. Okay, so how are we going to characterize fluids? If we're going to start applying the laws of mechanics to fluids, the first thing we say is they cannot support a shear. And having said that, for our next point, we're going to characterize them by a velocity vector. So as I said up here already, it's a field, and the field's going to be characterized by a velocity vector. Okay, so the velocity is a field, so it is a v vector of position, x, y, z, and t. And you could say at every point in your particular space here, so you're looking at some space, every point in that space, here's your x, y, z coming out of the board, every point in that space has a vector attached to it, so a three-component object that's a function of that position and time. Okay, that's the idea. So if you had a fluid flow, you can imagine all these vectors at each point here, and they could be of different lengths, directions, and so forth. Okay, so there's your characterization by velocity. Also, density rho, and rho will also be a function of x, y, z, and t. Okay, so there's a vector field, there's a scalar, and pressure P of x, y, z, and t. So the equations characterizing the change of these quantities in space and time will be partial differential equations. And actually density, pressure, and other quantities, I'm just going to write and other thermodynamic quantities principally. So pressure, density, entropy, things like that. And other quantities, let's go ahead and write them down. Quantities such as entropy, S, temperature, T. Okay. Good, so what else do we have? Am I numbering these things? I think so. Now, what does the role of the atomic nature of matter, what is the role of the atomic nature of matter? So atomism, I'll put a question mark there. So in our point systems, we thought we had a bunch of point particles. And in our continuum system, if we look close enough, it's a bunch of point particles as well. Okay. So the theory that we build up is going to treat these point particles that are the atoms, ultimately, atoms, molecules, as being so small that very many of them fit inside an infinitesimal element. So an infinitesimal volume element, we'll just call it d volume here. Okay, nothing to do with the velocity, d volume, delta volume. So this is very, very small on the one hand, but on the other hand, it still contains a very large number of atoms and molecules. So it's somewhere in between being truly microscopic and being macroscopic. So certainly the size of this thing has to be very small with respect to any dimensions, any other dimensions in the problem. Okay. So I'm just going to write this following. Infinitesimal volume element contains many particles. Okay, so from the standpoint of doing calculus, it's arbitrarily small. From the standpoint of actual structure of matter, it has to contain many particles. And finally, point 4, the forces between these particles are short range. That's actually very important. That's a very important assumption. Forces between particles are short range. Now, this deserves a red box around it. Because if you're talking about the physical assumptions and how they correspond to the mathematical assumptions we make, this is really important. So the forces between particles are very short range. That means that the forces acting, here I'll do these in red, on say neighboring infinitesimal elements, I'll just draw these two little cubes, okay? They act, since they're short range, they act from surface to surface, okay? And we'll actually make use of that in various and assorted derivations. So they're short range. So surface element acts on the other surface element. Say you're talking about the force of this particle on the one to the left, then it's via the surface. Okay. Now, long range would be if you had a fluid that's made up of ions, for example, charged particles, a charged particle fluid, solid, liquid, gas, plasma, right? That would be a plasma. And in that case, the equations that we're going to derive for these fields would have to include Maxwell's equations. And then instead of just fluid dynamics, you get what's called magnetohydrodynamics, which is vastly more complicated. Okay, so we'll save that for another day, so to speak. So that's the significance of the forces being short range. As soon as you have charged particles, those forces, Coulomb forces, are long range. That's a big difference. Okay, so we should even put that in our notes. They're short range, otherwise we have to include Maxwell's equations. In other words, otherwise meaning if we have charged particles. Okay. And that would give us this subject, magnetohydrodynamics. So if you hear the word, then you'll know what's going on there. Okay, good. So those are the prerequisites, so to speak, to setting up equations of motion for the velocity field. Okay, the next thing we're going to do is derive the continuity equation. And we could, in fact, add to this list here, but we'll just start a new heading. Actually, how about we do that? So 5, mass is conserved. So we're going to go ahead and start with the idea that mass is conserved in this fluid. And you can imagine a tapered nozzle. Actually, how about something that tapers, you've got a tube and it tapers and it opens up again, okay? So you've got 0.1 here, you've got 0.2 here, and if you have a fluid flowing through it, you've of course actually seen this before, it's going to speed up here, be slower here where the area is smaller. But the idea is the same amount of mass leaves as comes in, right? Same amount of mass enters the thing as leaves it. So let's see how we're going to write this down. So we've got this tapered pipe. Let V equal V sub x times I hat. So there's our x direction. So the mass that flows in equals the mass that flows out. So we will have rho V d area through A1 over here is equal to integral rho V d area through A2. And just to make sure we see that this is mass, we have mass, or actually I'm just going to do the dimensional analysis here. Kilograms per cubic meter, meters per second, and meters squared. Okay, so that's kilograms per second. So that's the mass that's flowing there through there per unit time. So that's the idea with the fluid flowing through here. Now let's make this a little bit more general. So generally, fluid flow through a bounded surface, okay, or through a surface that bounds a volume. Through a surface that bounds a volume. And we'll go ahead and use the boundary of the volume. I'm going to call del V0. That's the surface that bounds the volume. We will have density velocity. This is going to be a vector version of this expression here. Density velocity dot n hat dA, where n hat is the outer surface normal. Outer surface normal. So yeah, we've got some volume here and fluid flowing out of it. Outer surface normal is like that always. Okay. Those are n hat. So that's on the one side. On the other, I think I'll use this equation here. This is minus the integral. In fact, we've got room here. I'll write it down and then we'll explain it. E sub 0 rho d volume. Yeah. Okay, so this needs a little explanation. So this is clear. This comes right out of this idea here. Rho v dot n hat dA, so that's the outer surface normal. Now the outer surface normal dot dA, if everything's positive here, in other words, if we have V flowing out, then this is positive, but if something's flowing out of that volume, then there's a change inside that's negative, okay? Therefore, we put the minus sign in, change, and red density d volume is just the mass. So that's where that minus sign comes from. So it's the change of the total mass in that volume. And that's because that's the outer surface normal, okay? So good, we have this. And we're going to convert that now to a differential equation. So directly underneath here. Now we have a surface integral and a volume integral, and so we're looking at Gauss's integral theorem here. So we will have, I'm going to go ahead and switch the, so B0, I'll go ahead and put the derivative inside d rho dt dV over that volume, and then we'll apply the divergence theorem to this right side. I'll put the minus sign over there, and we will have V0 divergence of rho V. Okay. So here I just applied the divergence theorem, and I can bring this all under one integral. So let's make sure we note here divergence theorem. Gauss. And now we'll go ahead and put them all under one integral. D0 d rho dt plus divergence of rho v square bracket d volume equals 0. And now we're going to make an argument that's just like the fundamental lemma of the variational calculus. This is an arbitrary volume here, and therefore the integrand has to vanish. Okay. Since V0 is an arbitrary volume, we end up with d rho dt plus divergence of rho times v equals 0. And that's the famous continuity equation. There we go, that's not good. Continuity equation. Now you've probably seen something like this possibly recently in electricity and magnetism, because there's also a continuity equation there. So I'll just remind you of that, just to make the connection. In electricity and magnetism, this will be your charge density, and your charge density times V will be a vector as well. Current density. So yeah, let's just put that as a note. In E and M, d rho dt plus divergence of J equals 0, but J equals rho V is there the current density. Okay, so you've seen that before. Now we have an application that we're actually very important note here. We're going to go ahead and talk about Liouville's theorem that we had in classical mechanics a couple weeks ago, because we talk about incompressible fluids. Okay. So suppose our fluid is incompressible. That is to say, the density is constant. Okay. If the density is constant, then d rho dt is equal to 0, partial, and we can pull the density out of here, and then the divergence of the velocity is 0. There's a second important note. So this was just about E and M, but we're talking about this one right now. If our fluid is incompressible, density is constant, time derivative is 0, pull the constant out, differentiate, we have divergence of V is equal to 0. Now back in Hamiltonian mechanics, we had the phase fluid is incompressible and has a divergence equals 0. So I'm just going to write in Hamiltonian mechanics. You may remember I said I owe you this proof, and there are fancier proofs, but we're going to take this one. Okay. Divergence of Q dot P dot. So the divergence of this 2 n-dimensional vector is equal to 0. And we use that to claim that the phase fluid is incompressible and therefore it preserves volume. Okay. So, therefore, I'll put it in scare quotes, phase fluid is incompressible and therefore the phase flow preserves volume, which has interesting corollaries. I know a longer formal proof of this that doesn't leave Hamiltonian mechanics at all, but this is a good place to bring that in. Okay. Good justification for doing a little bit of fluid mechanics. Okay, so incompressible fluid, vanishing divergence. Okay, what else before we move on? Yeah, before I move on, applications of the continuity equation here, continuity equation. Really, the elementary ones are, for example, this nozzle phenomenon. You know, if you spray water out of a hose through a nozzle, it comes out much more rapidly where the cross-sectional area is smaller. So that's pretty basic, but this will also have other consequences later on as well. So we'll use it. So that's your basic corollary of mass being conserved continuity equation. Okay, so the next thing we're going to talk about is force. So this was from mass being conserved. So next, force and pressure. Force and pressure. Now we're going to be considering a little fluid element. Pressure is a scalar. Yeah, I'll just say pressure is a scalar. And the force, we know this is how we do this in physics 4A. Okay, so we have the pressure, force per area, and always acting perpendicular to a surface. So the force equals pressure times area, and if you want to put a vector on that, then you have to have a surface normal. Okay. But if you're going to have the surface normal and the force acting on some little volume element, then you actually have to put a minus sign in front as well. Example, and we'll derive this momentarily, but you have something floating. So you have something that can float in water, then you have all these, I'll draw them, you have pressures pushing on the sides, but then you have pressure times area pushing up on the bottom. And that opposes, and if it's just floating at rest, then equals the weight moving down. Okay. So here you're talking about buoyancy forces. And Archimedes' principle, which we'll get to formally in a moment, but that's just to jog your memory. So here we go. So for a volume within a fluid, so some volume within a fluid, there's a volume of a concrete object. Let's write down the net force is going to be minus integral P dA boundary of that volume for the reasons stated right here. Okay. Minus sign because of the outside surface normal. So I have to write here equals minus integral P n hat dA. Okay, so far so good. Pressure, surface normal, dA, minus sign, same argument as before. So next, we're going to multiply this vector, F net, by xi hat. So that's just a Cartesian unit vector, which means it's constant. Cartesian unit vector. And that will be F net I component of that vector there, because we're doing a scalar product. Over here it's going to be minus P n hat dotted into xi hat d area. This was on the boundary. Now we're going to do the divergence theorem again. Equals minus on the volume divergence of this pxi. Actually, yeah, divergence of. I could put these in this order as well. Xi hat dot m hat. Okay, because then this is the vector I'm talking about. So divergence of p xi hat d area. Okay. So what is the divergence of that vector in there? So we have to use an identity divergence P xi hat. So that turns a vector into a scalar. So that's going to be grad P, what do we have here? It's going to be grad P dot xi hat plus P times divergence of xi hat. So that's an identity, vector identity here. Okay, but the divergence of a constant vector is equal to 0. So we're going to end up with just gradient of P dot xi. So that's what remains in here over the volume. Good. So that was from one component. Okay. So we go back to F net. We end up with F net equals minus integral over the volume gradient P d volume. Because the gradient P xi hat is what went into here now. And so that was for the ith component. Go back to F net and you just got the gradient P dv. Okay, so we're ready to have Newton's law. Let me give an illustration though before we go on, because the minus sign is physically motivated now as well. Suppose we have, in the positive x direction here, an increasing pressure. Okay, so if pressure increases, then pressure's, okay, so let P increase with x. Okay, so pressure's increasing, and now just imagine a little object here. It means the pressure's higher on the right side than it is on the left side, and it's being pushed to the left, and F net is therefore minus this gradient here, right? Pushing to the left. Okay. So pressure is greater on this side, less on the other side, therefore it's pushed to the left. So you guys put that in words and put that in your notes. That's a good example. And actually, we can now use that for Archimedes' principle. Before we do any, I was about to go to Newton's law, but we'll do Archimedes' principle. No, Archimedes' principle comes a little later. Could do it now, but yeah, okay, good. So we are ready to do Newton's law. We now have the force on some little volume element with the fluid, and so we're just going to do the force per volume. So Newton's law. Now that we have our force law in the fluid, we have mass times acceleration is force. Actually, let's go ahead and write it this way. Mass times dv dt is equal to force. Okay. So what we're going to do for the mass is say we have density times, I'll use a delta volume, okay? Yeah, I'll use parentheses. So the density dV is our mass, dV dt, our acceleration. And for the force we have minus gradient of P, that's our vector. And then we also have a dV here, times dV. So this is when we go to an infinitesimal, so let's go ahead and write this for an infinitesimal element. Okay. Because then the dV's will cancel here. And we'll have a Newton's law. So we'll have, I think I'll divide by rho. Should I divide by rho? Not quite yet. So rho dV dt is equal to minus gradient of P. So that's Newton's law in a fluid, but it's not the form we're going to use it in yet. We have to do one more step on this. And the reason is, this is Newton's law for a fluid particle that is moving through space, but we have to express this as a field, okay? Because we're actually just talking about the behavior, since we're gonna have a partial differential equation, the behavior at and about a point in space, okay? So this has to be transformed, but it's just transformed with a big chain rule. So I'll do that next. So maybe I'll put a note here. Equation of motion for an infinitesimal fluid element. For this infinitesimal fluid element here. Okay. We're going to transform to a field equation. And to do that, we just have to do a chain rule. So continuing this thing here, let's say we have rho dvx dt is equal to minus dp dx. So that would be the one component, and there are three other components as well. So let's go ahead and do the chain rule on this. We're looking at dvx dt of x, y, z, and t, because this is supposed to be field. Okay. Well, we've done a lot of chain rule this semester, so that shouldn't be so bad. So we're looking at dvx dx and then dx dt. Since we're talking about a fluid particle, plus dvx dy dt plus dvx z dt, and then we have the explicit partial derivative as well, so plus dvx dt. So this dx dt, dy dt, dz dt will interpret as the velocity vector itself. So this is a v, and it's dotted into gradient of vx plus dvx dt. So this was just the x component, right? V dot the gradient of Vx. So we have a new operator actually. Therefore, if we want the whole vector expression, it's going to be this where we replace the Vx with the entire vector. So it's going to be V dot gradient applied to V plus dv dt. So that gives us all three of the components and not just one. Okay. When I say V dot gradient, it's V dot ddx. Okay. So this one you may not have seen before, where V dot gradient is this operation, Vx ddx plus dy ddy plus vz dz. So if we apply this to the vector v, we do it 3 times, and first with x we get this expression, and we get the corresponding y and z expression. Okay. Yeah. This, by the way, is why the mathematics of fluid mechanics becomes so difficult. This is going to be a highly nonlinear differential equation now, because we're going to take this expression and equate it to negative gradient rho. And I have room right here, but this is an important one. So we now have from here, okay, we'll do the dv dt is dv dt plus v dot grad v equals 1 over rho. So I brought the rho over, 1 over rho gradient p. Okay, fantastic. And this is the Euler equation. Euler was all over the place. The Euler equation of hydrodynamics and fluid mechanics, highly nonlinear because of this term right here. And but from the derivation we see it's Newton's law applied to an infinitesimal infinitesimal volume element, and then that is converted to a field equation right here. So that's the Euler equation. Euler equation. Let's see how we're doing time-wise. Okay. A lot more to say. Let me set this up now. Now we've got the Euler equation. It is Newton's law. Good. Yeah, let me set this up now. That's pretty systematic as far as where this comes from. But we'll state it again and make sure the various conditions are stated. Just formally and for the record, this is not an easy equation to get any solutions for. Okay. But we will get some. Good. So now let's just go ahead and I'm going to rewrite that. Our equation of motion grad applied to V minus 1 over rho gradient of P. So that's the first thing. Now, if there's gravity, if we have a fluid in a gravitational field, and that of course is pretty common, we can replace the right side with minus 1 over rho gradient P plus G, okay? That's just an added, would have come with an mg, so g is pointing whatever direction gravity is pointing. This, however, can be absorbed into the pressure expression G can be absorbed into the pressure if you want to have the simpler form of the equation. Okay. And when we do that, when we have to do that, we'll do that. Once we get Archimedes' principle, we'll see how to just incorporate that into the pressure for an incompressible fluid. Okay, so that'll be good. What else do we have here? Okay, so this is Euler's equation. It's for the motion of an ideal fluid. Ideal fluid, which is to say no friction, no internal friction, no dissipation. No friction, equivalent to saying no energy dissipation. Adding energy dissipation is a pretty complicated thing, but so ideal fluids will take us a certain distance. So no energy dissipation right there. And in fact, if you want to talk about this in more detail, you have to bring in some thermodynamics, because energy dissipation means that heat is generated, and you're in the continuum, so you have to talk about the thermodynamics of the fluid. So we'll keep it simple here for the moment. No dissipation. Lack of, okay, let me write this. So that means there's no viscosity, which is a measure of internal friction, no heat conduction. Okay. No viscosity, no heat conduction. And that means the entropy of a fluid element remains constant. Okay, so the entropy of a fluid element remains constant. Then we can say that S of X, Y, Z, and T is constant along the trajectory of a fluid particle, and we could call this entropy per unit volume. So S equals entropy density. I'm putting this down for completeness. We're not going to actually use these, but we will actually take this equation and take the complete time derivative of it, which is supposed to be 0, right? And then do another chain rule operation on this, and we see that we get gradient S dotted into V plus ds dt is equal to 0. Similar but simpler than what we just did a moment ago. You know, let me go ahead and write it this way. So we have, I'll just say ds dt equals 0, therefore this thing here is equal to 0. And if we take this equation, just for formal reasons, we'll use it later when we get to waves, but if we take this equation, we have 3 equations. That's a 4th equation, but we have S, rho, P, and V. Okay, so we have more quantities than we have equations. Okay. The reason, or to deal with that, we would have to invoke the thermodynamic relations between entropy, density, pressure. Okay. And before I forget, let's go ahead and write down continuity equation we already had. D rho dt plus divergence dot rho v equals 0. Good. So I have all of this up here. I'm going to just make a few closing comments on it, and then we'll have already gotten somewhere. So these equations here, Euler's equation, continuity equation, and this entropy equation are 1, 2, 3, it's a vector, that's a scalar, so 4, 5. Okay, so we have 5 equations. 5 equations for V, rho, P, S, which is to say 6 quantities. But these can always be linked by thermodynamic relations. Okay. For example, ideal gas law, that type of thing. And that will be your 6th equation. Okay, 5 equations equals 1 equation. So we have a complete set of equations that we can work with. The next thing to talk about is the incompressible fluid. And for the incompressible fluid, as we saw before, the divergence of V is equal to 0. So then we have the Euler equation, which is 3, and this equation, which is 1, so we have 4 equations. And since rho is constant, it's 4 equations for the 4 quantities. So incompressible fluid, divergence V is 0. So rho equals constant, divergence of V is equal to 0. Then we have this equation and the Euler equation, V dot grad V equals 1 over rho gradient P. So for the incompressible equation, it's these 4 equations for these 4 unknowns. So then you have a complete, I'll put a red box around there. Leave a little room under the red box because I have to mention the boundary conditions. Boundary conditions So at some fixed boundary that's not moving, we have v dot n hat is equal to 0. Okay. The dot product of the velocity field and the surface normal at a fixed surface is equal to 0. Okay, so there you have a complete set of equations that would characterize a whole bunch of fluid mechanical problems. They would be ideal, no viscosity, no heat conduction, and these would be the fluid flows. So I have one or two of these that we'll talk about next time. This is a good place to stop. Okay, so next time we'll review this stuff. We'll do Archimedes' principle, a couple of basic fluid flows, and then we're going to take the full set in order to talk about, well, that will probably be the time after next, to talk about sound waves. Okay, good. See you next time.